Alright, here we go with section 1.3. Now some of this you already know, so I'm going to skip through it, so you can go back and read it if you like, but when you see me skip something it's because you've already done that in like other classes and I know that you already know it. Because remember, this class sometimes it's for going through some basics that other people haven't been in, like pre-calculus or calculus or whatever, and haven't done these things. So anyways, so a matrix with one column can be called a column vector. So like these matrices you're going to start seeing represent vectors. So like 2, -3. So this could be like the vector 2i minus 3j. So you start seeing them listed like that. And a vector is usually named with a lowercase letter like v or u or some w or all those things. All right, so this part down here you already know. A scalar multiple, like when you multiply a number by a vector. So like, if you multiply these by -3 to get a new vector. So that would just increase the length of the vector. Actually, it would turn it around and increase the magnitude of it. This would increase the magnitude by 2. This is a linear combination of these two vectors. And so you guys already know how to do all that. So two vectors are equal only if the entries are equal. So that should make kind of sense. Over here, just like you saw in the video today as well, this is a geometric description of like adding vectors. So when you add one, and then you do the second one on the end of that one. So it's like you're taking a path, then you're adding this to the path, and so you get the resultant. So this guy right here, so basically instead of going this way and that way, you could have just gone straight over. So, I mean, this is just like the regular geometry picture of like adding vectors. Okay. The 0 vector is 0, 0, or however many you need. And you're going to see this a lot, this notation, R and like R2, up here talking about Rn. So that just matches the number of entries. So this is like in R2, so that's thought of as like 2 dimensions. R3 is 3 dimensions and so forth. So it's like the real number system for that many. All right, and down here, you know that. So Rn is just basically saying however many dimensions you need in the problem. Okay, so let's go on to the second page. So you pretty much know all of this as well. These are all just different vector operations. Obviously, when you add vectors, you can add them the other way and it doesn't matter. So, addition is commutative, multiply by a scalar. So these things you've seen before. And down here, getting to the definition of linear combinations. So a linear combination is any kind of like multiplying, adding two vectors together. All right, so not multiplying the vectors, but like let's say you had a vector, v1, and you did 3 times that, plus 2v2. This would be, the answer to this would be a linear combination of these two vectors. Okay, so this vector here would be these two things combined, right? And so this picture here, we're going to ignore for a second. I want to go down to example 2 because I have this picture kind of drawn out. So when we do our regular coordinate system, like 1, 2, 3, 4, and you talked about in the video I hat and j hat. This is our normal coordinate system. This is our normal xy plane, and our basis vectors are I hat, which is 1, 0, so that's our x direction, and j hat, not y, which is our y direction. So it takes us where we want to go in the y direction. Well, this over here is drawn a little bit differently. It's drawn with these basis vectors, 2, 1 and -2, 2. So every time you see something going 2, 1, so over 2, up 1, so this is red and this is pink here. It's kind of hard to see. So these lines going this way, these are all vectors. That space right there, that is taking you over 2 and up 1, over 2 and up 1. So these lines represent basically what would have been before, like x values, right? And then -2, 2, so the other lines, back to up to, these going this way, represent that. And so if I want to do something like I want to do 2v1 minus 3v2, all I have to do, I have to go 2 blocks on the V1 and minus 3 V2. So V2 would be going this way, so negative 2, 2, but I want to go the opposite way because I'm doing minus. So 3 of those, oh, I picked too big. So 1, 2, and the third would be like over here. So we can count these blocks are this amount, right? So we're going to use that to figure out this vector here. So this one says express each of the following as a linear combination of V1 and V2. So I want to know what can I do to V1 plus what can I do to V2 to get me 0, 3. So when I start looking at this, I'm like, oh, maybe I could just like add them together. All right, so like I want to get to the point 0, 3. So 0 and here is 3. Okay, so look, I could go this way. I could do a V1 and then I could do a V2. So I could basically, do you need this room?
Yeah, we can have it.
Okay.
How long will it be?
Oh, that's fine. I can go to across the hall. It's okay. Yeah, don't worry about it.
Before they go come to another 15 minutes.
Oh, okay. Can I stay in here until then?
Yeah,
all right. Cool. Thanks. Sorry. I was just finishing while they were doing that. So it's fine. All right. Okay, sorry about that. So we can kind of see that to get from here to here, following the blue lines, I can go this way and that way. So I can basically take a V1 and add a V2, right? So if I add those together, add these together, and then I get 0, 3. So we're going to say, just put like some 1s right here. All right, so V1 plus V2. All right, so the next one says, how do I get letter B? So negative 4, 1. So if I look over here, negative 4, 1 puts me right there. Oh, so I can see, why don't we do this and then go back the other way. So I want a negative V1, and so I go negative V1, and then let me add a V2. Let's check it out. So negative 2 plus negative 2 would be negative 4, and negative V1, so negative 1 plus 2 would be 1. Okay? All right. So for the rest of those, it's basically doing that same thing. So they're trying to get to 6, 6. So if you go to 6 and up to 6, you can kind of see, you can take a path. You can say, oh, let me go to the right. 1, 2, 3, 4. So 4 V1s, and then do a V2. So check it out. 8 plus negative 2 is 6, and 4 plus 2 is also 6. Okay, and then the last one's a little bit annoying. 7, negative 4. So if I go to 7 here and down to 4, where's 4? Across here. So right there. Okay, so for that one, let's see, I think I want to do a V1 plus, and then, I'm going to do minus because plus is going that way. So we'll do minus some V2s. So to get to here, I'd have to do 1, 2.5. So 2.5, so 2.5 V2s. So if you do that with these numbers here, you will get 7, negative 4. Okay. All right, so that's how you use those pictures like that. It's just kind of, you see those often. All right. So write a system of equations that's equivalent to this vector equation below. So when you do that, so basically you would say, okay, well, I have negative 2x1, so that one, plus 8x2, so this guy, plus 1x3 equals 0, right? And then down here I got 3x1 plus 5x2 plus, minus x3, or 6x3 equals 0. So in linear algebra, a lot of times there's like, all these different ways to write the same thing. So this is just like the vector way of writing this problem right here. All right, and so down here, write this equation in a vector system. So we're going to go backwards. So I need a vector for x1, and the numbers that go with it are 4, 1, 8. and then plus, and we'll do one for x2, is 1, negative 7, 6. All right, and then for x3 is 3, negative 2, 5. All right, then equals, and then the answers. So 9 to 15. So these are like interchangeable, right? If you're given this, you can make it that, and vice versa. All right. So anytime you get something with the same solution set, you know that that the matrix, it came from the same matrix. So let's go to example 5. Determine if B is a linear combination of these three things. So we want to know if this matrix here is in some way a combination of these three things. So what we do when somebody asks me this question, I put this 1, negative 2, 2, 0, 3, oh, 0, 5, 5, sorry, 2, 0, 8. I augment it with this. I want to see if I can use these numbers to get that answer, negative 5, 11, and negative 7. Okay, and then you row reduce it. When you row reduce it, you get 1, 0, 2, negative 5, and then you get 0, 5, 4, 1, then you get 0, 5, 4, 2. Actually, you just do a couple steps there. I didn't do it in the calculator. So look at this right here. Look at this mismatch. Same matching numbers, but different here. So we'll have to say no. There's no solution to this. So my answer to this question would be no. This vector is not a linear combination of these right here. All right, so for example 6, determine if B, so same question as this one. So when this one works out, we'll just skip this one, but same basic idea. Okay. So if something is a linear combination of other vectors, then we say that it is in the span of those vectors. So a couple things there. So when a vector is in the span of other vectors, that means that it is a linear combination of those vectors. So span is a big word that you start to hear over and over and over again. Like, is this in the span? Is this a linear combination? Those are the same questions, just different phrases. Okay, almost done here. So this top part, you can read it. This was explained kind of in the video. You saw that a lot, so these pictures kind of are similar to those. And so let's go down to the questions here. Number 7. For what values of h is y in the plane generated by v1 and v2? So we're going to set up a matrix. 1, 0, negative 2, negative 3, 1, and 8. Augment it with this, h, negative 5, negative 3. So I want to know when is this in the span of these, basically. So for this one, we have to do by hand since we don't have a calculator for us. So I'm going to tell you that if I do 2 times row 1 plus row 3, that's my first move. I'm going to get 1, negative 3, and h. Sorry, I'm going to use this room, so I'm trying to go fast. All right, so when I do that, I get 0, 2, and 2h minus 3. So I'm just going to divide these by 2. So this will turn into a 1, and then I'll have that. So if I want this thing to work, then I need these last 2 rows are basically copies of each other. I need this expression here, 2h minus 3 over 2, to equal negative 5. Like, they need to match so that I don't have like a no solution situation going on. So I got 2h minus 3 equals negative 10. Add 3. And then, so my answer is h has to be negative 7 over 2 if this is going to work. All right, and then the last one here. So this is saying let W be the set of all linear combinations of A is B and W. So is this a linear combination of these? So again, you just set up your matrix. You put 10, 3, 3 here. You row reduce it. When we row reduce it in the calculator, you get 1, 0, 3, 5. 0, 1, 1, 1, and the last row goes away. So yes, there is a solution. So my answer to this is yes, it is a linear combination. In fact, there's infinite solutions. All right? And show that the third, oh, we're not going to do that part. Okay, so asking someone if something is a linear combination of something, or if something is in the span of something else, then those are basically the same question. Okay? All right, so I'll see you in class. You'll do section 1.3 in class, but this video and 1.2 bookwork is your homework. Bye-bye.